Hey folks, how are you? I just watched this version of this video from last year, 2 years ago, and boy, was it unbearable. I'm going to try to talk faster, but not too fast. So, we're talking about rotation, and now we've spent some time talking about systems in equilibrium, where net torque is zero. And we've solved a bunch of problems with Plancks and that are just sitting there. And now we're going to talk about rotational acceleration, and Newton's second law. Newton's second law, regardless of what context you talk about it in, is about what controls or maybe affects a system's acceleration. All right. Now, linearly or translationally, we mean, if there is an object that maybe all it can do is accelerate along this, along a path. I could even simplify this and say, here's an object that has no shape at all. Here's that object. Well, what controls its acceleration? Two things. One of them is, well, like that. And the other one is that. All right, how much force do we apply to this object, and what mass does the object have? Right, mass being, well, I should really sort of say net force. Mass being, well, mass having to do with inertia, right? How difficult is it to make something accelerate? All right, and well, the relationship that ties these things together is Newton's second law, net F equals ma. Because what controls acceleration? Well, A depends on net F and mass. How hard do we push? And to what degree does this object, this point mass, resist acceleration? All right. On the angular or rotational side, well, there are some analogs. All right. We can no longer say here's just a thing, a single object, a single simple point mass. Maybe this mass or this thing has some shape and size. It has to have some shape and size now. And so, well, what we get to is that there's angular acceleration. I'm going to go right from here and try to draw an analogy, and that is that angular acceleration, well, guess what? Depends not on net force, but on net torque. And, well, again, there's some thing that goes in here. Well, I'll call it resistance to alpha, right? In the same way that mass in the bottom of this Newton's second law expression is resistance to linear or translational acceleration. There's something that goes down here that is really the rotational analog of plain old mass. That's about how much do objects or systems resist angular acceleration. All right. Hopefully you're okay with the fact that the more torque you apply to an object, the more or the faster its angular velocity will change. Now remember, right, alpha by definition is the rate of change of angular velocity. So if we want to change an object's angular velocity, well, apply a net torque. We want to change that angular velocity fast, apply a lot of net torque. All right, but sometimes even if we were to apply a lot of net torque, an object or system maybe still won't have a large angular acceleration because there's a big resistance to that angular acceleration. So let's talk about what that rotational analog of mass is. So let's take a system like this. Here's a point mass, M. Ooh. And it's on the end of this massless rod. The massless rod part is important because it's just kind of like it's not there, but it keeps this thing a certain distance. Let's call it R. It keeps this thing a certain distance from this axis of rotation. So really, well, this is actually like a vector R, right? Now, from a linear translational standpoint, I mean, we can draw currently a free body diagram for that object. All right, and this thing is released, and so for at least for an instant or a couple of instants before this thing starts to move along an actual curved path, it'll just accelerate straight down. All right, and so we can say that net force equals ma, or we can say that mg equals ma. All right, this object will have a translational acceleration equal to g. It's in free fall until this rod starts doing its thing and making this object change directions, then things change. All right, now rotationally or angularly, we can take this mg equals ma, and just because why not, sort of, let's multiply by the magnitude of that vector r. All right, now notice this, we sort of said, well, I'm just doing it because I feel like it, but now this is force times r. And it's the only force acting on that object, and it's at a distance r from that axis of rotation. So this is actually the net torque acting on that object. All right. Now, this acceleration is an acceleration along the path. It's a tangential acceleration. So this right side we can rewrite as, well, AT is R alpha. And here's our other R. So look what we have now. We've actually gotten to an expression that has net torque. It has alpha, right? Like we were talking about, let's find this expression that relates that kind of stuff. And so the rest of that expression on our next page is what goes in here. And that is, well, the M, the R, and the R. All right, equals mr squared alpha. And so in this case, this is what goes in the rest of that expression for Newton's second law, mr squared. Except that it's not always just mr squared, because this is for a point mass only. All right, but what we're going to do is we're going to refer to this as that other part of the Newton's second law equation. We're going to call this net torque is alpha times this stuff, and that stuff gets called I. All right, and that's our rotational analog for mass. This is a lot like, it has a very similar structure to the equation net force equals ma. All right, but this is our angular version of Newton's second law. All right, and it means that these two quantities are analogous. All right, so the rotational analog of mass is called, well, is I, and it's called one of two things: rotational inertia and or moment of inertia. All right, and it's entirely about, just like kind of plain old M is, it's entirely about the degree to which a system resists angular acceleration. All right, now remember, this rod here up here was massless. So that, because it's massless, it has no resistance to anything. All right, but for our, for our point mass here that is moving or starts to accelerate, the moment of inertia, or the rotational inertia for that point mass, we just showed is this, mr squared, where r is, importantly, distance from AOR to the mass. Fair enough? So we have what we can put into our expression for Newton's second law for rotation. I'm going to clean this up a little bit. What we say for Newton's second law for rotation is that net torque is I alpha, and or that angular acceleration is net torque over rotational inertia. All right. If we want to have lots of angular acceleration, well, you could either apply a lot of net torque to some system or find a system with very small resistance to angular acceleration. All right. So this is our expression for Newton's second law for rotation. Okay, so let's spend a little time on the rotational inertia stuff. All right, here's an object that's a 350 gram point mass revolving around an axis in a 2 meter radius circular path. Sure. Okay, so this point mass, point mass, is just mr squared, where r is this dimension here. Right, so that's 350. Well, I turned it into kilograms, most likely, times 2 meters, and we'd square that. So 3.35 times 4, because we're squaring that 2, that's 0.7, 1.4 kilogram meters squared, right? Don't forget we have to square those units. Okay, here's 2 point masses. Let's call them like, how about M1 and M2, and we'll say that they both revolve around this central axis, this one at a distance r1, this one at a distance r2. Well, this 2 mass system has, I don't want to really go there. Let's say I total is I point mass 1 plus I point mass 2. All right, and that would be, well, m1 r1 squared plus m2 r2 squared. Fair enough? Okay. Now, different, maybe we'll, hang on, let's get back to that. Here's a system that's, well, this thing is not a massless rod. This yellow thing is a rod that has a mass m, and it's has a length L, and then here's an actual non-point mass, but a thing, a ball, a sphere of radius R and mass M, and this form is going to swing around this axis. So at some point later, this whole dealio will be over there because the whole thing is rotated. All right, now this rotational inertia, this system's rotational inertia, or moment of inertia, it's not just mr squared because, well, mr squared is for a point mass, and this thing, these forms are not point masses. So what you can be given, what you will be given in lots of cases are expressions for common moments of inertia, or this is moment of inertia. But we should probably say rotational inertia also. But those are interchangeable. I'll say them interchangeably, right? Moment of inertia or rotational inertia, but I don't want to write RI. Anyway, so here are a bunch of kinds of things that typically rotate about typical axes, like a cylinder rotating about an axis, like a hoop, like a can that you cut the lids off of, and that rolls about its center. Sure, a solid sphere. Here's a rod that spins around an axis in its center. Here's a rod that spins about an axis at its edge. A little bit less. I mean, this would be like a coin, like, you know, a cylinder. A coin's a cylinder, just a short one. This would be like a coin that's spinning on a table. All right. Here's a shell, a hollow sphere. All right. Notice one big difference. All right. These circular things are about the dimension r, the radius of the circle-y part. All right, r. These things that are sticks are about L, the length of the whole thing, the length of the thing. All right, so this has a length L. This has a length L. Spheres don't have lengths, they have radii. All right, these rods don't have radii, even though they look like it's a little circle here. Forget about that. What we care about is the length of the thing. Okay? Yeah, here's, you know, notice that this is just like this. It's a cylinder just squished. They're both 1/2 mr squared. Very common ones here. These are very common to use. The sphere will certainly do a bunch. The hoop, that. We don't do this too much. We don't do this too much. The shell, you know, once in a while, it's like a basketball rolling. Okay. So what is this thing made of? All right, we want to write an expression for this system's total rotational inertia. All right, so, well, I would say that this, you know, maybe I system is, what is this thing? Well, it's a rod about its end, right? This is the rod part about its end. Well, it's also plus, now check this out. This thing we can treat in two ways. All right, we treat it as an object that moves in a circular path, right? And so for that reason, we can treat it like a point mass. This thing swings in a big old circular path that brings it around here and then back over there. And so for that reason, that sphere is like a point mass that moves in a circular path. But it's also a sphere, all right? And notice, like, here's a place on the sphere. When this thing, assuming there's a rigid connection here, which there is, when this form swings around 180 degrees, look where that red dot gets. It gets over here. So what is that sphere doing? What is it doing? The sphere is rotating about an axis that goes through its own center. All right, because this point doesn't stay on, quote, the right side of the sphere. It stays on the outside of the path. So the sphere is rotating. So I'm going to say what we have to add is a term for the sphere about its axis. All right, so how do we do all these things? Well, I of a rod about its end, if you refer back to the reference, is 1/3 ml squared, right? M and L. Now, the fact that the sphere moves in a circle, that means we just do mr squared. All right, well, that's m. Now, what's r? R, by definition, is radius of circular path. And if we're real careful about this, this radius of the circular path that the sphere moves in is this. And so that's actually L plus the radius of the sphere. And then the fact that this thing is a sphere, and let's say it's a solid sphere. All right, we're going to say this thing is solid. That says solid. The moment of inertia of a solid sphere about its central axis is 2/5 mr squared. Okay, so complex forms can have complex expressions for their rotational inertias, where you have to take each individual part's rotational inertia and add them up. All right, again, you might also have to say an object that moves in a circle might be an object that is actually spinning as it goes around in the circle, and just kind of like a point mass that moves in a circle. So this is point mass in circular path, and this is object rotating. Okay? Okay. So, Newton's second law. When an object accelerates in a straight line or travels along a path and changes direction, or, you know, is translating, Newton's second law says that net force equals ma. All right? Or that acceleration is dictated by net force and mass. When an object rotates about an axis and has an angular acceleration, we use a different form of Newton's second law, which is that net torque is I alpha, or angular acceleration is completely dictated by the amount of net torque applied and the system's rotational inertia. Those are these are sort of the forms that you'll use when you're solving problems. This gets to, you know, the actual meaning. It's about what affects acceleration. Okay, so let's talk a couple of different situations where we can apply this idea. And let's say that here's a regular door, top view, here's the hinge, all right? And this door has a width W. And we're going to apply a force here to open the door. All right, well, here's a force F. We can write a net torque analysis for this door using Newton's second law. All right, so our net torque is, well, W times F. It's R times F perpendicular, and we've just said that, let's just say those are perpendicular. Is I alpha? Well, I for this form is, well, this is a rod about its end. Even though it's a door, we don't care about the dimension that comes in and out of the page. We care about the width. And so that's 1/3 M W squared times alpha. All right, so there is an alpha here. We can write an expression for alpha. Notice that one of these factors of width go away, and we get that alpha is 3F over MW. Yes? Yes. Now, let's say that we have a door of the same mass, but this one swivels around its center. Right? And let's say that we want to get the same exact alpha. And the question is, how much force do we need to apply? And let's say that we're going to apply the force to the end, to the edge. Right? And I'm going to call this, there's some new force that I'm going to call, how about like F prime? So we're going to write a net torque statement for this form. All right, so our net torque is now, well, here's vector R from axis of rotation to point of application. All right, so that's R. Well, remember, this is the same size door, so this is W, right? So our R is W over 2 times our new F, what we called F prime, here's our new torque, equals, well, this is a rod that spins about its center. Moment of inertia is 1/12 M, well, still W squared, right? Again, we use the whole dimension of the door, of the rod, and then times alpha. Well, algebra saith we can take a factor of W out of there. We can take this, well, this is supposed to be a 12th, 1/12. And we can take, well, a 2 and a 2. There's a 6 remaining over there. And so what's our new F prime? All right. Well, our new F prime is how much force do we need? Well, we need a force that's F prime is 1/6 M omega alpha. So how's that compare to the other case? Well, F from over here, F is 1/3 F, sorry, 1/3 MW alpha. All right, so notice that now we can apply a force that's 1/2 as much. All right, because this system, this door is easier to rotate, right? It has a smaller rotational inertia. This rotational inertia is 1/3 ml squared. This rotational inertia is 1/12 ml squared. Now this says, look, this is like 4 times easier to rotate than this. So how come it's not 1/4 the force? Well, because notice we apply our force at half of this other distance, and therefore this force produces only half the torque that the other force produces, but this is 4 times easier to open, and the result of it all is that, we need half the force that we originally needed. Okay? Okay, here's your job for my people that I see soon. You will write some expressions for the following. All right? Let's say that this dimension is R, all right, the radius of this disk. And then this dimension here is 1/3 of that. All right. Originally or initially, there's going to be a force Fe that we're going to say acts here. You write me an expression for angular acceleration. All right. Then there's going to be another force F that's applied somewhere on this dotted line such that the disk no longer accelerates. All right. And let's assume that that force F is applied tangent to that circle. You write me an expression for how big F is. All right. And then we change F to F prime. Now, F prime might be bigger than F, might be smaller than F, but you now write a new expression for what this disk's angular acceleration is now. Okay? So, this has been an introduction into Newton's second law for rotation, which is about what affects objects' angular acceleration. All right? So, maybe not super new that net torque is part of the puzzle, but hopefully super new is that there's something called rotational inertia, which is about how much systems resist accelerating angularly. Okay? And we'll write lots of net torque analyses for objects that are not in equilibrium, but now we can use those analyses to generate expressions for how fast they change angular velocity, because that's the definition of angular acceleration. Okay? See you soon.